Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 30, SR Latch, for chapter 6, flip-flops for the course Digital Logic Design or Digital Systems or Digital Electronics. This lecture is extremely important because really it's the foundation of latches and flip-flops. And the next slide is a disclaimer for you to read. I cite 3 references in digital logic design, but there are many available online on the internet. Chapter 6 contents included sequential networks, synchronous versus asynchronous, mode versus melee, and memory elements. And today we will talk about the SR Latch. What's latch and what's the difference between a latch and flip-flop? A latch is a level-sensitive binary storage device implemented with a limited number of logic gates. It may have a clock or may not have a clock. The simplest latch is composed of 2 cross-coupled NAND or gates. On the other hand, the flip-flop is a more sophisticated, clocked, edge-triggered binary storage device widely used in practice. So it is not a level sensitive like the latch, it is edge triggered. It is either positive edge when the signal moves from 0 volt to 5 volt, or the triggered at the negative edge when the signal or the clock moves from plus 5 volt to 0 volt. There are 4 common latches and flip-flops. They are set reset or SR, trigger or T, delay or D, and JK flip-flop and JK flip-flop and latches. The SR latch has 2 inputs S and R and 2 outputs Q and Q prime, where the output Q prime is the complement of a Q. That is, if Q is 1, Q prime must be 0 and vice versa. Therefore, the SR latch has 2 states defined by Q is equals to 1 or Q prime is equals to 0, referred to the 0 states, and Q equals to 1 or Q prime is equals to 0, and this is called the 1 state. Now, if the latch at the 0 state without any excitation, the latch will stay at the 0 state indefinitely until the inputs has been changed. The same thing with the 1 state, so both states are stable state. So the latch remains in one stable state indefinitely until the inputs S and R are changed to do otherwise. Since the latch has 2 stable states, it's called a binary or bistable multivibrator. In electronics, there are 3 types of multivibrators: a stable, not stable, multivibrator, which is generate a square wave clock shape, and monostable or unstable state, and bistable, which is the SR latch. The inputs S and R are either pulses or voltage levels, while the outputs Q and Q prime are usually both voltage levels. So when we say the output Q is 0, it means 0 volt. When we say the output Q is 1, it is 1 volt. Now the next slide will show us actually the block diagram, the latch of the SR latch, and its logic symbol, which is the block diagram, where we see the inputs S and R and the outputs Q and Q prime. Now those are the latch designed with 2 NOR gates and with 2 NAND gates and inverter. They are cross-coupled NOR gates, where the reset is on the top, applied to the upper NOR gate, and the set applied to the lower NOR gate. The output Q, which is, and Q prime. Now this output Q, we call it the present state. When we observe the output Q at a specific moment of time, the output Q will be the present state. Now, once we apply the inputs, the output Q will change to Q plus. So Q plus will be the next state. So Q, we call it the present state, before the application of the inputs. But once we apply the inputs, S and R, we observe the output Q and we call it Q plus. So it will be the next state. Q prime must be the complement of Q all the times. So if this is a Q, Q prime is the complement of Q. If this output, which is from the same location, Q plus, after a specific amount of time, after the application of the input, the output here will be Q plus prime. So Q and Q plus are measured and observed from the same pin, from the same location, which is the upper NOR gate or the upper NAND gate. Now, if you look at the implementation, the hardware implementation with 2 NOR gates, we said the reset applied to the upper NOR gate and the set to the lower NOR gate. And here, S and R are inverted, so we are applying S prime to the upper NOR gate and R prime to the lower NAND gate, again to get Q and Q prime. Now, what's my inputs to the latch, to the SR latch? My inputs, not only S and R, it is S and R and the present state Q. What's my output? My output is a Q plus. My output is a Q plus. Now, to understand how the latch works, we need to understand the NOR gate and we understand the NAND gate. Let's start with the NOR gate and let's understand how this circuit B will work to generate what we call the detailed truth table, the SR latch. So this is the detailed truth table of the SR latch shown here, with the input SRQ and the output Q plus. And the compact table will be SR and Q plus as a function of Q0 and 1. Okay, so this is what we call it, actually the mode of the set reset latch. Okay, we are coming to this soon. To understand how we derive this table, which is extremely important, SRQ, we should understand the NOR gate. The NOR gate, which is the complement of OR gate, will give me 1 when both inputs are zeros, and give me 0 otherwise. So if we apply 0, 0 to the NOR gate, the output of the NOR gate will be 1. If you apply 0, 1, 1, 0, or 1, 1, the output of the NOR gate will be 0. So let's stay with the NOR gate circuit first, with circuit B. Now, to do actually the experimentation, we will take S and R to logic switches, and we will force the output Q to be 0 or 1 at a specific moment of time. So at a specific moment of time, Q can be either 0 or 1. So if we apply S and R to both zeros, and we said those comes from logical switches, and Q, and we observe the change in Q. So initially we will set Q to be 0. Q prime must be equals to 1, and we are applying 0, 0. So the upper NOR gate, if this is 0 and this must be 1, Q prime must be 1, then the upper NOR gate will have 1 NOR 0, because R is 0, which is 0. So the next state, Q plus, will remain 0. So if we started with 0, it will remain 0. Now 0 NOR 0 will be 1. So Q prime plus will remain 1, will be 1. So Q changed from 0 to 0, and Q prime changed from 1 to 1. It remained 1. By doing this, we have proved actually the first line in the table. So if we have SR 0 or zeros, and Q is 0, Q plus remains 0. We are not showing a Q prime. We could Q prime and Q plus prime, okay, for simplicity. To make the table, we could add really 1 column Q prime and 1 column Q plus prime if you wish, okay, to see the change. So we have proved that this line, the first row in the table, it's a correct row, because when you apply 0, 0 and q was 0, q plus 0. So there is no change. Now let's repeat the experiment. We will set the q at we will observe the q at specific time t to be 1. Now at this time, if this is 1, if a q is 1, a q prime must be 0. So in the upper NAND gate, we will get 0. Again, R and S is still zeros both. We'll apply R and S to zeros from logical switches. So we will have the upper NOR gate. We will have a 0 here. 0 NOR 0. You will get 1. So Q plus will be 1. It was 1 and it will remain 1. Now the lower NOR gate, 1 NOR 0, we will get 0. So Q plus prime will remain 0. So when we have 1, we can repeat the cycle. The upper will be 0, NOR 0 will give me 1, 1 NOR 0 will give me 0. So it is a stable state. We can repeat if you want to see whether it's stable state or not. And by doing that, we proved the second row of the truth table. When we have 0, 0, 1, again, we will achieve 1. Now, in the compact truth table, we will have SR an input and a Q plus. So since Q plus is equal to Q, Q plus is equal to 0 when Q is 0, Q plus is equal to 1 when Q is 1. So what we say Q plus is equal to Q. When S is equals to 0 and R is equals to 0, Q plus is equals to Q, and this is, we call it the hold mode. The hold mode. You hold the data, the same data, when S and R are zeros. Now let's go and check the next row, the third row, when we changed R to 1. Okay, again, we will force the circuit to have a Q0 or a Q1. When Q is 0, Q prime will be equals to 1. And here we set R is equals to 1 and S is equals to 0. So in this case, in the upper node, since this is 0 and this is 1, the upper node will give me 1 node 1 and this will be 0. So Q will change from 0 to 0. So Q plus will be 0. And 0 node 0 will be 1. So Q prime plus, or the Q plus prime, will be 1. So what this will verify the next row of the table. So we applied 0, 1, and Q was 0, Q plus remained to be 0, Now I will repeat the experiment with Q is equals to 1. So Q1, Q prime is 0, R is 1, and S is 0. So in the upper NOR gates, and this is 1 and this is 0, 0, NOR 1, the output will be 0. So Q plus will be 0, or the Q change from 1 to 0, or the Q plus is equals to 0. Now the lower NOR gate, since this is 0, 0 NOR 0, NOR 0 because S is 0, the output Q prime, which will become a Q prime plus, is 1 because 0 NOR 0 is 1. So Q changed from 1 to 0, while Q prime changed from 0 to 1. So what this tells me that when Q is 1, okay, Q plus, or the Q changed, and this is the fourth row. When 0, 1, it is 1. Q plus became 0. And Q plus prime is 1, became 1, which is the complement of 0. Okay, now those two rows, which is 0, 1, 0 and 0, 1, 1, where the output became 0, could be rewritten as S is 0, 1, and Q plus is 0 all the time, or we call it the reset mode, the reset mode. Now, let's verify the next line of the table when S is 1 and R is 0, and we will study the case when Q is 0 and Q is 1. Let's start with the Q is 0. Let's go back to the circuit. Now, in this circuit, we have S is 1 and R is 0. If we assume Q to be 0, okay, and we look at the lower node, so 0, this is 1. If Q is 0, Q prime is 1. The lower node will be 0 node 1, because this is 1. 0 node 1 is 0. So Q prime will change to 0. Q prime plus becomes 0. 0 node 0 is 1. So what we get, Q changed from 0 to 1, or the Q plus will be 1, and the Q prime plus will be 0. And this is precisely this row. So when we applied 1, 0, and Q was 0, Q plus became 1. Q plus became 1. We'll repeat the experiment when Q is 1. When Q is 1, so Q prime, when Q is 1 and Q prime is 0, and S is 1 and R is 0. So we have S is 1, R is 0. Okay, what we say? So we have 1 node 1 will give me a 0. Will give me a 0. And 0 node 0 will give me 1. So the 1 will remain 1. So this is a stable state, and this will verify the next row. So the next row, when we have 1, 0, 1, Q plus remained 1. So what this tells me, these two rows, when we have a 0, change to 1. When we have a 1, change to 1. So we have, when S is 1 and R is 1, Q plus always will be 1. So in the compact table, when we have 1, 0, Q plus is 1, and this is, we call it the set mode, Now the problem will appear in the last two rows of the SR detailed truth table. When S equals to R, X equals to 1, see what will happen. And why this is a big problem, because this is what we call it, inputs are not allowed because we will have an invalid state. Okay? So let's go back to the diagram. Now, R is equals to S, R equals to 1, and S is equals to 1. We'll apply them from logic switches while Q is 0. So when Q is 0, Q prime has to be 1. Q prime has to be 1. And in the upper node, you will have 1 node 1, because this is 1. 1 node 1, so you will get a 0. Now 0 node 1, because S is 1, will be also a 0. What you will get? You will get a Q plus 0, and you will get a Q plus prime is 0, and this is invalid because we cannot have anything like that. Q prime always must be the complement of Q. So this is, we call it invalid state, because Q plus and Q plus prime, both of them became zeros. Let me repeat the experiment when Q is 1. So this is, before we repeat the experiment, this is really verify this one. When we have 1, 1 and 0, we say don't care because this is invalid state, or the inputs must not take place, or S must not equal to R equal to 1. Okay, that's what it means. Let me repeat the experiment with Q is 1. So when we have 1 and R and S, both of them are 1s. In the lower node gate, we have 1 node 1, so you'll get a 0. and 0 nor 1 will give me a 0. 0 nor 1 will give me a 0. 0 nor 1 will give me a 0. So again, you will find q plus and q plus prime, both of them zeros. And this is invalid. So what we say here, we say that the 1, 1, when s is equals to 1 and r is equals to 1, we will say we have an invalid state. Now this is why we will replace this flip-flop with other flip-flops that we don't have this problem with. But if you ask me, why do we use the SR latch or SR flip-flop? Simply because it is the price issue. It is very cheap, much cheaper than the other flip-flops and latches. So we verified the detailed table in depth and the compact table with using NOR gates. We can do the same thing with NAND gates. We can do the same thing precisely with NAND gates. So the only difference here, we inverted S and R. But before we do that, we need to understand the NAND gate. The NAND gate will give me the output to be 1 when the inputs are 0, 0, the two NAND gates, 0, 0, 0, 1, 1, 0. And give me the output 0 when both inputs are 1, 1. So this is, we covered this before, the NAND gate. And we will study those cases one by one. Again, let's go to the detailed table, and from the detailed table, we will see the following. So let's apply 0, 0, and we will have a 0. When we apply 0, 0, so when apply S and R 0, 0, we are applying 1, 1 to the NAND gates because those are inverted. So S in this case will be equals to, S prime will be equals to 1, and other prime will be equals to 1, 2. Okay? So we are applying 1 to the upper NAND gate and 1 to the lower NAND gate. Let me assume Q to be 0. Now when Q is 0, and we are applying 1 and 1 to the NAND gate, one NAND, if we look at the upper, let's look at the upper NAND gate first. We have a 0, NAND 1. 0 NAND 1 will give me a 1. 1 NAND 1 will give me the output here, a 0. So when the output is 0, when Q is 0, when Q is 0, the upper, and this will be 1, we said 1 NAND 1 on the upper NAND gate will be 0, and 0 NAND 1, which is the input to the NAND gate, other 0, so other prime will be equals to 1. Okay, so we'll have a 0 NAND 1 will give me 1. So the Q plus is 0 and the Q plus prime is 1. Okay, so let me repeat. The Q initially 0. We have S equals to R is equals to 0. So the S prime is 1 and other prime is 1. If this is 0, this must be 1. And 1 NAND 1 on the upper NAND gate will be 0. And 0 NAND 1 on the lower NAND gate will be equals to 1. So Q has not been changed, or we say Q plus will be equals to 0. And this will verify the first row in the table. When we have 0, 0, 0, Q plus will be equals to 0. Let me assume now Q is 1. When you assume Q is 1, the lower NAND gate, again, R is 0, so R prime is 1. if one NAND 1 on the lower NAND gate will be 0. So Q prime will be 0. 0 NAND 1 will be 1. So Q plus will remain 1 and Q plus prime will remain 0. And this will verify the next row. If 0 is 0 and Q is 1, Q plus 1, and this will verify the hold mode in the table. When S is 0, R is 0, Q plus will be equal to Q. Okay, so this circuit works precisely like the two coupled NOT gate, cross-coupled NOT gate. So the two cross-coupled NAND gate with two inverters is identical to the two cross-coupled NOT gate. But you have to pay attention that we are applying S to the upper part of the circuit, R to the lower part of the circuit, unlike the NOT gate where we apply R to the upper side of the circuit and S to the lower side of the circuit. Now, with this, actually, we go to the next line. So we proved one mode. We go to the next line. We are applying S0 and R is 1. S0 and R is 1. And we will study Q is 0 and Q is 1. Okay. Again, when S is 0 and R is 1, it means S prime is 1 and R prime is 0. So the upper NAND gate will have 1 here, and the lower NAND gate we have one input will be a 0. Now if Q is 0, Q prime must be equals to 1 by definition. So the lower NAND gate will have 0 NAND 0, which is equals to 1. Okay, 0 NAND 0, which is equals to 1. And 1 NAND 1, because it's 0, so S prime is 1. 1 NAND 1 is equals to 0. So all this tells me that Q plus is 0 and Q plus prime is 1. So the two output, the 0 will remain 0 and the 1 will remain 1. No change, right? So all this will prove this row of the table, that we have 0, 1, 0, the output remains 0. Now let's study if Q is 1. If Q is 1, again we are applying 1 to the upper NAND gate from S, because S prime is 1 and other prime is 0, and here we have 1. So Q is 1, Q prime is 0. In the lower NAND gate, we say 1 NAND 1, so you will get, so 1 NAND 1. Let's look at the lower NAND gate, 1 NAND 0, because R is 1, so we are NANDing with 0. So 1 NAND 0 will be equals to 1. And 1 NAND 1 on the upper, because S is 0, so S prime is 1, so 1 NAND 1 is 0. 1 NAND 1 is 0. So Q plus is 0, and Q prime plus is 1. Q prime plus is 1. So what we proved that when Q is 1, okay, it will change, the next state will be 0. So 0, 1. 0, 1, 1 will give me Q plus 0. So since we have both zeros, okay, regardless of the value of Q 0 and 1, we say this is the reset mode. So if S is 0 and R is 1, if S is 0 and R, Q plus will be equals to 0, or this is the reset mode. Let's do the next two lines. We are applying S is 1, which is the set mode, and R is 0 in both lines, where Q is 0 or 1. Now again, those will be inverted. So what we are applying basically, we are applying to the upper NAND gate 0, because S prime is 0. And to the lower NAND gate, we are applying a 1. Okay? let's see what the set mode works. So when Q is 0, if Q prime will be equals to 1. So the upper NAND gate will be 1 NAND 0, which is equals to 1. Okay, so Q changed here from 0 to 1. Okay, and the lower NAND gate will have 1 NAND 1 because of the 0. So this is 1, the input to the NAND gate. So Q prime will be 0. And this will prove the law. This is the Q changed from 0 to 1. Changed from 0 to 1. So this law 1, 0, 0, Q plus is 1. Okay, let's do with Q when Q is 1. Let's see, it must remain 1. So again, when we have 1, we have the input to the upper NAND gate 0, the input to the lower NAND gate is 1, which is the complement of R. So when we have here 1, the lower NAND gate will have 1 NAND 1, the output will be 0, and 0 NAND 0, because S is 1, the output will be 1. So Q remains, Q plus is 1, and this will verify the next line in the table. So 1, 0, 1 remained 1. Since for these two rows, Q plus is 1, regardless on the value of Q. So we said when we have S is 1 and R is 0, the output will be 1, and this is the set mode. Now the two invalid lines, okay, inputs not allowed, we are applying S is equals to R is equals to 1, or S prime is equals to other prime is equals to 0. So to the upper NAND gate, we're applying a 0 here, and we're applying a 0. So let's start with the Q0, and Q prime is 1. So in the lower NAND gate, so we'll have 0, NAND 0 is 1, and 1 NAND 1 is, so 0, NAND 0 is 1, and 0 on the upper NAND gate will have 0, will have 1 NAND 0, 1 NAND 0, and will give me 1. So what we will get? We will get Q plus is equals to Q plus the prime is equals, let me repeat the experiment again. We are applying 1, 1 here, so the NAND gate will have zeros of their inputs. So if this is a 0, 0 NAND 0, you will get 1. And this is 1, 1 NAND 0, you will get 1. So you'll have 1 here and 1 here. And if we can repeat this circle again, okay, or the cycle again, okay, so you get 1 NAND 0, you will get 1. And 1 NAND 0, you will get 1. Okay, so if we change the Q from 0 to 1, so if we start with 1, 1 NAND 0 is 1, and 1 NAND 0 on the upper NAND gate is also 1. So regardless if the Q is 0 or 1, okay, the two Q plus and Q plus prime, they will be equal, and they will be equal to 1. And this is invalid because it's against the definition of SR Latch and SR flip-flop. Q prime has to be always equals to Q, the complement of Q, and Q plus the prime has to be always equal to the complement of a Q plus. And this is the invalid state. Now, once we have the truth table fully verified, and we verified those fully in details, okay, we can come and we can derive the characteristic equation of the SR Latch. So we can go to KMAT with the input SRQ and Q plus. Those are don't care because this will never occur. And we will have SR0, 0, 0, 1, 1, 1, 0, Q0, 1. We have 0, 1, 0, 0, 1, 1, and don't care. We have a set of 4 and a set of 2, okay? as a product term. So the set of 4 will give me the 0, will cancel the 1 for the R, so I will get S. 0 will cancel on the vertical side, so we'll get S or R prime Q. R prime Q. This is, we call it the characteristic equation of the SR Latch. From the characteristic equation, we can get what? The truth table if you want to. Okay, and from the truth table, we got the characteristic equation. Also, we concerned a lot about what we call it the excitation requirement of SR Latch, or the excitation table. What's the excitation table? Give me the transition between Q to Q plus, 0 to 0. What do I need the excitation to be to achieve a 0 if the output was 0? Or to achieve a 1 if the output is 0? Or to achieve a 0 if the output is 1? Or to achieve 1? So the excitation table will be a normal truth table with the inputs Q and Q plus 0, 0, 0, 1, 1, 0, 1, 1. And what we need S and R. To understand this, we go back to the detailed table. Look at the transition from 0 to 0 occurred when S is 0 and R is 0 in the first row. The transition from 0 to 0 will occur also on the third row, when S is 0 and R is 1. What it means? That S must be 0 all the time, but R could be 0 or 1, or R don't care. So we come here, we have S is 0 and R don't care. Let's look at the transition from 0 to 1. 0 to 1. The transition from 0 to 1 will occur, we go back to this detailed table. 0 to 1 will occur right here, okay? When we have S is 1 and R is 0. Does it occur anywhere else? 0 to 1, Q 0 to 1. It does not. So 0 to 1 occur only once, and to do that, the transition table, the excitation table will give me S has to be 1 and R has to be 0. How about the transition 1 to 0? We come again to the detailed table. 1 to 0. 1 to 0 will take place here when I have S is 0 and R is 1. Does it occur anywhere else? 1 to 0. 1 to 0. 1 to 1. 1 to 0. 1 to 1. It does not. So 1 to 0 occur only once. 1 to 0 occur only once when S is 0 and R is 1, and we put it here. In the excitation table, 1 to 0, we need S 0 and R is 1. How about 1 to 1? 1 to 1, very interesting. 1 to 1. 1 to 1 will occur here, okay, in the second row when S is 0 and R is 0, and will occur here when S is 1 and R is 0. It means S either 0 or 1, but R must be 0. So this will be don't care, 0. So S don't care and R must be 0. So once we have the excitation table, we can draw the state graph. We have two stable states, 0 and 1. Now, if the transition will occur between 0 to 0, 0 to 0, we need S to be 0 and R don't care. So we will remain at 0 with the transition from state 0 to state 0. With the transition from state 0 to state 1, we need 1, 0. 0 to 1, we need this, see, the row here, okay? The other row, and what we write on the other, 1, 0, because S needs to be 1 and R to be 0. Now from 1 to 0, if we go back to state 0, we need 0, 1. So we have 0, 1 on the other. And if we remain at state 1, from 1 to 1, what we need, S is don't care and R is 0. So we got what we call it the state graph of the SR Latch. Now, the next slide, and this is the last slide, which is the timing diagram, the SR. The timing diagram, which is a graphical representation for the truth table, okay? Again, how the truth table will work and how the output, how the next state will work. So what we have, if we assume the latch delay time is negligible, the latch responds immediately to the set and reset excitation SNR. The timing diagram for S latch is shown where the latch changes state according to the inputs S and R. If the latch in state 0 and S is excited, the latch goes to state 1 and remains in state 1 until R is excited. Once R is excited, the latch remains in state 0 until S is excited again. So it is a very simple way. So this is an example for excitation of S and R arbitrarily chosen. Okay, so we have S connected to logic switches and we set it at a specific amount of time. And when R is 0 and S is 1, we will find Q will go from transition from 0 to 1. It will remain 1 until we hit R will be active, will be excited. When R is excited, we'll find Q, the output of the latch will go to 0. But if S is excited again, activated again, okay, we'll go back, Q will go back to 1, and so on and so forth. So this is how the timing diagram gives me an understanding, graphical understanding how the SR latch is working. And this is, there's no clock pulse, this is unclocked SR latch, the most primitive, and we cover the SR latch in entirety. The most important thing is it's a truth table, it's compact truth table, and how we drive it from the hardware, which is the 2 NOR gate and the 2 NAND gate and inverters, and also how we derive the characteristic equation, the excitation table, and the state graph, and also the timing diagram latch. This will be the conclusion of this important lecture of the SR latch, and I thank you so much for listening. Please subscribe if you didn't do so by clicking on the blue circle. Hopefully to see you soon. Sincerely, Dr. Hassan.